Close your eyes. Go ahead, close them, and try to imagine nothing. Not nothing in particular, but genuine nothing. Absolute emptiness. The complete absence of everything. Take your time. Empty your mind of stars, of planets, of the coffee cup on your desk, and the floor beneath your feet. Remove the air, the light, the faint hum of electricity. Strip away space itself until you are contemplating what exactly? If you are like most people, you have just pictured a vast, dark emptiness, a kind of cosmic warehouse with the lights switched off and all the furniture removed. Perhaps infinite blackness, silent and still, waiting patiently for something to happen. I'm afraid I must disappoint you. You have not imagined nothing. You have imagined something pretending to be nothing. Consider what you actually conjured. Darkness. But darkness is something. It is the visual experience of no light reaching your eyes. That experience requires eyes, a brain to process signals, and a universe in which light could, in principle, exist, but happens not to be present. Darkness is not nothing. Darkness is something very specific. Or perhaps you pictured empty space, a vast expanse with no objects in it. But space is something. It has dimensions. It can be measured. It curves in the presence of mass. Empty space is not nothing. It is a stage upon which things could happen. A stage is furniture. Here is the strange thing. Every attempt to imagine nothing smuggles something in through the back door. We cannot picture absolute emptiness because the picture itself requires a frame. Where is your imagined nothing located? In some mental space. And that space is something. When is your nothing existing? For some duration. And time is something. The very act of imagining creates a container, and a container is not nothing. This is not a failure of your imagination. This is a clue. We take nothing to be the simplest concept imaginable. The default state, the blank page, the empty vessel. Children understand it easily. The cookie jar contains nothing. The toy box is empty. What could be more obvious? But notice something curious about these examples. The empty cookie jar is still a jar. The vacant toy box is still a box. In each case, nothing means no things inside a space that still exists. We experience absence within presence. We never experience the absence of presence itself. Let us try a thought experiment. Imagine a room. Remove the furniture. Remove the air. Remove the walls. Remove space itself. Remove the possibility of space. Remove what is left to remove. Notice the moment your imagination fails. That boundary marks the edge of conceivable existence. You cannot picture nothing because nothing, properly understood, may not be something that can exist at all. The universe, it seems, shares our difficulty. As we shall see, physics suggests that true nothing, absolute emptiness, the complete absence of everything including space and time, may be impossible. Not merely hard to achieve, but forbidden by the fundamental laws that govern reality. Your cognitive inability to imagine nothing is not weakness. It may be the most accurate intuition you possess. We have uncovered a puzzle where we expected only simplicity. The word nothing sits comfortably in our vocabulary, domesticated and harmless. But examined closely, it reveals depths we never suspected. If we cannot imagine nothing, and if physics suggests nothing cannot exist, then what fills the void we naively call empty space? To answer that question, we must first understand why our intuitions betray us, why our confident sense of what nothing means fails so spectacularly when applied to the cosmos. We find ourselves in a bewildering situation. The simplest concept imaginable, nothing, turns out to be inconceivable. How did our minds come to possess a word they cannot actually comprehend? The answer lies in how we learned the word in the first place. As children, we understood nothing through absence. The cookie jar is empty. The hiding spot contains nothing. The glass has no milk left. These experiences trained our brains to think of nothing as simple lack, the default state when something has been removed. This training served a purpose, an extremely practical one. Consider your distant ancestors on the African savannah 200,000 years ago. When they checked behind a rock, they needed to know if danger lurked there. Nothing dangerous meant safety. They didn't need to contemplate whether the space behind the rock was seething with quantum fluctuations. They needed to know. Tiger. No tiger. That's all. Evolution optimized our brains for survival, not for physics. We are exquisitely tuned to detect medium-sized objects at medium speeds over medium distances. We see the tiger in the tall grass. We notice when fruit has been taken from the branch. We remember where we left useful tools. We are, quite literally, walking tiger detection devices pressed into philosophical service. Is it any wonder we struggle with quantum mechanics? The scales at which quantum effects dominate, 10 to the negative 35 meters, are as far below human experience as the observable universe is above it. Our brains evolved in the comfortable middle, where objects have definite positions, causes precede effects, and empty means empty. When we try to extend concepts that work brilliantly at human scales to the quantum realm or the cosmic scale, they break. Solid objects are mostly empty space. Simultaneous events depend on who observes them. Up and down have no meaning in orbit. Nothing joins this list. Useful locally, misleading universally. Here is what makes this particularly treacherous. The errors feel like common sense. When something feels obvious, so obvious that questioning it seems foolish, we should be especially suspicious. The sun obviously orbits the Earth. You can watch it move across the sky. Objects obviously fall because they seek their natural place. What else would they do? Time obviously flows at the same rate everywhere. How could it be otherwise? Nothing is simple, feels equally obvious, and it is equally wrong. Notice how your concept of empty always implies a container, an empty glass, an empty room, an empty parking spot. In each case, there is a space that could contain things, but currently doesn't. The emptiness exists within something, bounded, defined, waiting to be filled. We have no everyday experience of emptiness without a container. We have no intuition for the absence of space itself. When physicists began probing reality at its smallest scales in the early 20th century, they discovered something deeply unsettling. The vacuum, what we casually call empty space, would not cooperate with common sense. Classical physics had suggested that if you removed everything from a region of space, all matter, all radiation, all energy, you would be left with genuine emptiness. A perfect void, the ultimate nothing. Quantum mechanics disagreed. The disagreement was not subtle, it was fundamental. And it arose from a principle that initially seemed to concern only measurement, but turned out to concern existence itself. If neither imagination nor evolved intuition can grasp true nothing, we need new tools. We need physics, the systematic study of what actually happens, regardless of what our savannah-bred brains expect. What does physics actually say fills the void we call empty? What seethes in what we naively call empty space? The answer will require us to understand something called the uncertainty principle. And the uncertainty principle will reveal that perfect emptiness isn't just hard to achieve. It is forbidden, by the fundamental structure of reality. In 1927, the German physicist Werner Heisenberg discovered something that would transform our understanding of emptiness forever. The discovery seemed, at first, to be about measurement. It turned out to be about existence itself. Heisenberg's uncertainty principle is often stated like this: you cannot simultaneously know both the position and momentum of a particle with perfect precision. The more accurately you pin down one, the more the other slips away. Most people who have heard this think it means our instruments disturb what they measure, that the act of observing nudges particles around, introducing unavoidable error. This interpretation is profoundly wrong. The uncertainty principle doesn't say we cannot know a particle's exact position and momentum. It says the particle doesn't have an exact position and momentum at the same time. The fuzziness isn't in our knowledge. It is in reality. This is deeply counterintuitive. We are accustomed to thinking that properties exist, whether or not we measure them. The moon, Einstein objected, doesn't cease to exist when no one looks at it. But at the quantum level, properties we take for granted, position, momentum, energy, are not fully determined until observation forces them to be. What does this have to do with nothing? Everything. The uncertainty principle doesn't apply only to position and momentum. It applies to energy and time as well. And this pairing has consequences for the vacuum that our intuitions never prepared us for. Here is the key insight. We cannot specify that a region of space contains exactly zero energy for any significant duration. The very act of specifying precisely zero for a measurable time violates the uncertainty principle. The more precisely we try to say zero energy here, the more the energy must fluctuate. Empty space cannot be still. The laws of physics forbid it. Think of it this way. Imagine someone who borrows money and repays it so quickly that their bank balance never officially goes negative. The briefer the loan, the larger the amount they can borrow without the bank catching the discrepancy. If they borrow and repay within a millisecond, they might temporarily possess a fortune, all while their account statements show nothing unusual. The vacuum works similarly. It constantly borrows energy from the uncertainty principle and repays it before the cosmic accounting catches up. The briefer the loan, the more energy can be borrowed. This manifests as particle-antiparticle pairs flickering into existence and annihilating each other within timescales too short to directly observe. We call these virtual particles. The name is unfortunate. It suggests they are imaginary, theoretical, not quite real. This is misleading. Virtual particles have measurable effects. They are as real as the consequences they produce. Consider the Casimir effect, first predicted in 1948 and measured experimentally since. Place two parallel metal plates extremely close together, nanometers apart, in the best vacuum you can create. The plates will attract each other. Something pushes them together. What pushes them? Nothing. Or rather, nothing. The vacuum itself. Here is why. Virtual particles of all wavelengths constantly appear in the vacuum everywhere, but between the plates, only wavelengths that fit exactly between them can exist. Longer wavelengths are excluded. Outside the plates, all wavelengths appear. This means more virtual particles press against the plates from outside than push from between. The imbalance creates a measurable force. The vacuum is not empty. It pushes things. Engineers designing microelectromechanical systems must account for the Casimir effect. At very small scales, the vacuum's restlessness becomes a practical engineering constraint. Nothing has become something they must design around. There are other confirmations. The Lamb shift, a tiny discrepancy in hydrogen's spectrum that classical physics cannot explain, arises from virtual particles briefly affecting the electron. The anomalous magnetic moment of the electron, measured with extraordinary precision, matches theoretical predictions only when virtual particles are included in calculations. The vacuum churns, it fizzes, it seethes with activity so furious that if we could perceive it directly, we would find ourselves staring into a blizzard of particles appearing from nowhere and vanishing before they can be properly counted. Imagine the most perfect vacuum chamber ever built, colder than intergalactic space, emptier than the voids between galaxy clusters. Even there, quantum mechanics demands activity. The chamber is silent to our instruments, but deafening at the quantum scale. There is no way to make it truly quiet. The uncertainty principle forbids perfect stillness. We thought nothing was passive. It is violently active. We thought nothing was simple. It is ferociously complex. We thought nothing was the absence of physics. It is physics at its most fundamental. The vacuum is not the absence of everything. It is the presence of possibility, energy fluctuating, particles appearing and disappearing, activity that never ceases, because cessation would violate the laws that govern reality. But normally, these virtual particles annihilate each other harmlessly. They borrow energy and repay it. They appear in pairs and cancel in pairs. Under ordinary circumstances, the cosmic bookkeeping balances. What happens when something prevents the repayment? What occurs when the delicate balance is broken? When virtual particles are torn apart before they can annihilate? The answer lies at the most extreme boundaries in the universe, the edges of black holes. And the answer reveals that the vacuum is not merely active, it is creative. Black holes are defined by a single, absolute property. Nothing escapes them. Their gravity is so intense that the escape velocity exceeds the speed of light. Since nothing can travel faster than light, nothing gets out. Not light itself, not information, not anything that crosses the boundary we call the event horizon. This is what makes the name black hole so apt. They emit no light. They are holes in the observable universe, regions from which no signal can ever return. Or so we thought. The vacuum, it turns out, has something to say about this. Consider what happens near a black hole's event horizon. The vacuum there, like everywhere else, seethes with virtual particle pairs appearing and disappearing. Normally, these pairs emerge together, exist for an imperceptibly brief moment, and annihilate each other. Energy borrowed and repaid. Cosmic books balanced. But the event horizon creates a unique situation. Imagine a virtual particle pair appearing just at the edge of the horizon. One partner slightly inside, one slightly outside. The inside partner is immediately captured. It falls into the black hole, past the point of no return. The outside partner, suddenly lacking its annihilation mate, finds itself alone. It has nowhere to go, no partner to cancel against. The debt it owes cannot be repaid through mutual annihilation. So the universe does something remarkable. It converts the virtual particle into a real one. The outside particle escapes into space, carrying energy away from the vicinity of the black hole. From a distance, it appears that the black hole has emitted radiation. Black holes glow. This is called Hawking radiation. And it doesn't come from inside the black hole. Nothing escapes from there. It comes from the vacuum itself, responding to the extreme curvature of space-time at the event horizon. Let me be clear about what this means. The radiation is not leaking out of the black hole. The event horizon remains absolute. Anything inside stays inside forever. Instead, the vacuum at the boundary manufactures particles from its endless activity, and some of those particles escape. The ultimate consumers of matter and light are slowly consumed by creative nothing. Think of virtual particle pairs as couples joined by mutual debt. Under normal circumstances, they must stay together to balance what they have borrowed. The event horizon acts as a divorce lawyer with cosmic authority. It can separate them permanently. One partner falls past the horizon, the other is left outside, holding claims that the universe must honor. The debt that was meant to cancel instead creates a real particle where none existed before. The implications are extraordinary. First, black holes have temperature. The radiation they emit corresponds to a thermal spectrum, exactly what you would expect from an object with a definite temperature. For a black hole with the mass of our Sun, this temperature is extraordinarily low, about 60 billionths of a Kelvin, far colder than intergalactic space. But it is not zero. Black holes are not perfectly cold. They radiate. Second, black holes evaporate. Each escaping particle carries energy away. Energy and mass are equivalent. Einstein's famous equation applies. As radiation carries energy outward, the black hole loses mass. Given enough time, it loses all its mass. It evaporates completely. The timescales involved stagger comprehension. A solar mass black hole would take roughly 10 to the 67th years to evaporate, a number so large that the current age of the universe, 14 billion years, is essentially zero by comparison. We will not observe stellar black holes evaporating, but smaller black holes, if they exist, would evaporate faster. And in the final moments of any black hole's life, as it shrinks to subatomic scales, it would release tremendous energy in a burst of radiation. The principle matters more than the timescale. What can leak will eventually be gone. Black holes are not eternal. Nothing truly lasts, not even the things that seem most permanent. Third, and most profound, the boundary between virtual and real is not absolute. Under ordinary circumstances, virtual particles remain virtual. They borrow and repay, appear and disappear, leaving no lasting trace. Under extreme circumstances, the virtual becomes actual. What was merely potential becomes genuinely real. The vacuum is not just active, it is creative. Given the right conditions, it transforms possibility into actuality. We have now seen the vacuum's creative potential demonstrated at the most extreme boundaries in the universe. But this raises a deeper question. If virtual particles churn everywhere, if the vacuum has energy, how much energy does nothing actually contain? And what does that energy do to the universe as a whole? The vacuum is not empty. We have established this, but we have not yet asked, how much not empty is it? The answer depends on who you ask. And the disagreement between the two best answers we have is, quite possibly, the worst prediction in the history of physics. Start with what we can measure. In 1998, astronomers observing distant supernovae made a startling discovery. The expansion of the universe is accelerating. This should not happen. Gravity attracts. Every galaxy pulls on every other galaxy. The mutual attraction should slow the expansion, like a ball thrown upward, gradually decelerating as Earth's gravity pulls it back. For decades, cosmologists debated whether the universe contained enough matter to eventually halt its expansion and collapse, or whether it would expand forever, but at an ever-slowing rate. No one expected it to speed up, yet it does. Distant galaxies are flying apart faster and faster with each passing cosmic moment. Something is pushing, Something pervades all of space, exerting a kind of pressure that accelerates the expansion rather than slowing it. The leading candidate for this mysterious something is vacuum energy, the energy contained in empty space itself. How can empty space contain energy? We have already seen how the quantum vacuum seethes with virtual particle activity. This activity carries energy. The energy exists everywhere. Space exists. And vacuum energy has a peculiar property. Unlike normal matter or radiation, it does not dilute as space expands. Consider normal matter. As the universe expands, the same amount of matter occupies a larger volume. The density decreases. But vacuum energy is a property of space itself. As space expands, more space exists and more vacuum energy exists. The total amount increases. The more space you have, the more vacuum energy fills it, the faster expansion accelerates, creating more space, creating more vacuum energy. The fate of everything, galaxies, stars, planets, atoms, may depend on the properties of nothing. We call the measured energy density of the vacuum the cosmological constant. It's tiny, but not zero. Astronomers have measured it through observations of cosmic expansion, the cosmic microwave background, and the large-scale distribution of galaxies. The measurements agree. The vacuum has energy. Now here is where the humility comes in. When physicists attempt to calculate vacuum energy from first principles, adding up the zero-point contributions from all quantum fields, they get a number. A very large number. A number roughly 10 to the 120th power, times larger than what we observe. 10 to the 120th. This is not a small disagreement. If you predicted your commute would take 10 minutes and it took longer than the current age of the universe, that would be an enormous error. But it would not be this error. This discrepancy is so vast that ordinary language fails to convey it. Something cancels almost all the calculated vacuum energy. We do not know what. We have ideas, supersymmetry, anthropic selection, modifications to gravity, but none are confirmed. The cosmological constant problem remains one of the deepest unsolved puzzles in fundamental physics. What should we make of this? The honest answer is, we understand enough to know the vacuum has energy, and we understand enough to know we don't fully understand it. This is how science works, not through sudden complete comprehension, but through gradual illumination of mysteries that reveal deeper mysteries. We solve the puzzle of why the vacuum is not empty. In doing so, we discovered the puzzle of why its energy is so much smaller than calculations predict. Each answer reveals new questions. The universe does not owe us simple resolutions, but let us not lose sight of what we do know. The vacuum has energy. That energy pervades all of space. It appears to drive cosmic acceleration. The fate of structure in the universe, whether galaxies will eventually fly apart, whether stars will die alone in an ever-emptying darkness, depends on properties of the vacuum we have not yet fully understood. Nothing has consequences, enormous ones. If the vacuum contains energy, and that energy shapes the evolution of the cosmos, we must ask the ultimate question. We have seen the vacuum's creative potential at black hole boundaries, virtual particles becoming real, nothing becoming something. Could this creative potential extend not just to particles at the edges of black holes, but to the universe itself? Could everything have emerged from nothing? We have traced nothing from comfortable misconception to quantum reality. We have seen the vacuum seethe with virtual particles, watched those particles become real at black hole boundaries, and discovered that vacuum energy may shape the fate of the cosmos. Now, we must ask the question that all of this has been building toward. Could everything, the entire universe, with its hundreds of billions of galaxies, each containing hundreds of billions of stars, have emerged from nothing? The question sounds absurd. Something from nothing violates our deepest intuitions about causation. Every effect has a cause. Everything comes from some prior thing. The chain of causation cannot begin from nothing, because nothing has no causal power. Nothing, by definition, cannot do anything, or so we assume. But we have already seen our assumptions about nothing fail catastrophically. We assumed nothing was simple. It is ferociously complex. We assumed nothing was passive. It seethes with activity. We assumed nothing was achievable. It appears to be forbidden by the laws of physics. Perhaps our assumption that nothing cannot produce something is equally mistaken. Consider a curious feature of the universe. Gravity contributes negative energy. This requires explanation. When you lift a book, you add energy to it. Gravitational potential energy. The higher the book, the more energy it possesses. But here is the strange thing. We define zero gravitational potential energy as the state where objects are infinitely far apart, not interacting at all. When objects fall together under gravity, when they bind into systems, they release energy. The bound system has less energy than the separated components. This means gravitationally bound systems have negative gravitational energy compared to the unbound state. Now think about the universe as a whole. It contains enormous positive energy, all the mass of stars and galaxies, all the radiation, all the kinetic energy of motion, but it also contains enormous gravitational binding. Every galaxy pulls on every other galaxy, every star on every star, creating a vast web of negative gravitational potential energy. What if these cancel exactly? What if the total energy of the universe is precisely zero? This is not philosophical speculation. It is a possibility that physics permits, perhaps even prefers. And if the total energy of the universe is zero, then its existence requires no external input, no energy needed to be injected from outside, no primordial push was necessary. The cosmic book's balance. Think of it this way. Imagine creating a hill by digging a pit beside it. The dirt removed from the pit forms the hill. You have created something impressive, a hill. But the total amount of dirt is unchanged. Positive and negative cancel. The hill and pit together sum to flat ground. The universe may be the ultimate hill and pit. Matter, energy, radiation. These are the hill, impressive and visible. Gravitational binding is the pit, invisible but essential. Together, they sum to zero. If so, the universe is the ultimate free lunch. You can get something spectacular from nothing if the something cancels to nothing. But how does a zero-energy universe arise from genuine nothing, not empty space, but the absence of space and time altogether? Here, quantum mechanics re-enters. We have seen that the uncertainty principle forbids perfect stillness, perfect certainty, perfect emptiness. Even nothing, whatever primordial state preceded the universe, cannot be perfectly stable. It must fluctuate. Normally, quantum fluctuations are tiny and temporary. Virtual particles appear and disappear. Small amounts of energy are borrowed and repaid. The fluctuations average to zero over time. But what if, very occasionally, a fluctuation doesn't average out? What if the borrowed energy takes a form that can sustain itself? A bubble of space-time that under the right conditions expands rather than contracts, inflates rather than annihilates. This is the hypothesis of quantum cosmogenesis. the universe as a quantum fluctuation that persisted. The primordial nothing from which the universe emerged was not empty space. Empty space is already something, already a stage with dimensions and properties. Primordial nothing was genuine, nothing, no space, no time, no dimensions, no laws, no properties at all. And yet, even this nothing could not be perfectly stable. Quantum uncertainty applies to existence itself. Fluctuations must occur, and occasionally, perhaps inevitably, given infinite opportunity, a fluctuation nucleates a bubble of space-time. If that bubble's total energy is zero, it needs no external cause. If conditions within the bubble trigger rapid expansion, what cosmologists call inflation, the bubble grows exponentially, cooling and differentiating into the structures we observe. Galaxies, stars, planets, and eventually, beings who wonder where it all came from. The universe needs no external creator because it creates itself. It requires no first cause because its own existence is the cause. The laws of physics permit a cosmos to bootstrap itself into being from the creative potential inherent in nothing. This is not mysticism. This is where the equations lead. Is it proven? No. We cannot directly observe the universe's origin. We cannot replay cosmic history in a laboratory. But the physics allows it. Something from nothing is permitted if the something balances to zero. The most fundamental question, why is there something rather than nothing, may have an answer within physics rather than beyond it. And that answer may be, because true nothing is impossible, because nothing must fluctuate, because occasionally fluctuations persist. We are, quite possibly, living inside a quantum fluctuation that refused to go away. We have traced nothing from cosmic misconception to the possible origin of everything. But physics that remains abstract, disconnected from daily experience, is physics that fails to illuminate. Let us bring this home, quite literally, to the table in front of you, the chair beneath you, the hand you might reach out right now. Press your hand against a surface. Feel the solidity, the resistance, the undeniable presence of something substantial pushing back. What are you actually feeling? Not what you think. The table is made of atoms. So is your hand. And atoms are mostly empty space. If an atom were the size of a football stadium, its nucleus would be a fly at the center, a single fly in a vast arena. The electrons would be gnats somewhere in the stands, not orbiting in neat rings like textbook diagrams suggest, but existing as clouds of probability, more likely to be found in some places than others, never precisely located until observed. Between the nucleus and the electrons, nothing, or rather the quantum vacuum, seething with virtual particles, active and restless, but containing no solid matter whatsoever. How empty is an atom? If you removed all the empty space from every human being on Earth, all 8 billion of us, the remaining matter would compress into a volume smaller than a sugar cube. Everything we are, physically, is almost entirely not there. Yet the table feels solid. Your hand does not pass through it. What stops it? Not matter touching matter. Your hand's atoms never touch the table's atoms. They don't come close. What stops your hand is force, specifically electromagnetic repulsion between electron clouds. When your hand approaches the table, the electrons in your hand's atoms and the electrons in the table's atoms begin to overlap in proximity. Electrons, being negatively charged, repel each other. More importantly, the Pauli exclusion principle, a fundamental quantum rule, forbids electrons from occupying identical quantum states. As electron clouds try to occupy the same space, this prohibition creates enormous resistance. What you feel as solidity is the universe enforcing a rule about what electrons can and cannot do. You never touch the table. You feel the table's rules pushing back. Consider what this means. The sensation of solidity, perhaps the most visceral confirmation we have that the physical world is real, is not caused by substance, but by force. Not by matter, but by law. Not by stuff, but by structure. The solid world is built on rules operating in mostly empty space, and that empty space is not truly empty. It is the quantum vacuum, the same vacuum we have spent this documentary exploring. The virtual particles flickering between your hand and the table are the same virtual particles that create Hawking radiation at black hole boundaries, the same fluctuations whose energy may drive cosmic expansion. The quantum vacuum is not exotic physics happening in distant laboratories or at the edges of black holes. It is the substrate of your existence. The empty space within your atoms is active, restless, creative nothing, the same nothing that may have given birth to the universe itself. You are held together by quantum mechanics. You exist because the Pauli exclusion principle prevents matter from collapsing into neutron star density. You feel solidity because electrons repel at a distance, never touching, following rules that govern the vacuum they inhabit. The next time you doubt that physics concerns your daily life, remember, you are not touching the chair you sit in. You never have. You are hovering above it, suspended by electromagnetic negotiation between electron clouds, held together by rules, built mostly from restless nothing. What seems most solid is constructed from emptiness. What feels most substantial is almost entirely not there. This is not a metaphor. This is what you are. We have seen that the quantum vacuum is creative, seething with activity, producing real particles at black hole boundaries, possibly birthing universes from fluctuations. We have seen that matter is mostly vacuum, held together by forces and rules rather than substance. But does this have any meaning beyond physics? Is there any connection between the creative nothing that underlies particle physics and the emptiness we encounter in daily experience? The silence between notes, the space between words, the pause in conversation? The question might seem like a stretch. Physics is physics. Art is art. Meaning is something else entirely. To draw connections between quantum mechanics and musical rests might appear to be the worst kind of poetic overreach. And yet, consider what music actually is. Notes, vibrations at particular frequencies, arranged in patterns over time. But music is not only the notes. Remove the silences from a piece of music. Connect every note directly to the next, with no gaps. And what remains is noise. The silences are not absences from the music. They are part of the music, as essential as the sounds themselves. The pause allows the previous note to resonate. The rest creates anticipation for what comes next. The silence provides the contrast against which the sound becomes meaningful. We cannot perceive continuous sameness. A sound that never varies becomes background, inaudible. A light that never changes becomes invisible. Only difference registers. Only the contrast between something and something else, between presence and absence. Meaning requires absence. A sculptor understands this intuitively. They do not merely carve a figure, they carve the space around it. The negative space, what is removed, what is not there, defines the positive form. Without absence, there is no presence. Without emptiness, there is only undifferentiated block. Text works the same way. The words you are reading exist only because of the white space around them. Remove the margins, the spaces between words, the gaps between paragraphs, and the text becomes unreadable noise. Meaning emerges from the structure that emptiness provides. The physicist discovers that the vacuum is creative, that nothing seethes with potential, that emptiness can birth reality. The artist discovers the same truth through different means, that silence makes music, that negative space makes sculpture, that margins make meaning. The parallel is structural, not mystical. I am not claiming that musicians are doing quantum mechanics or that poems literally contain virtual particles, but both domains reveal a common truth about how reality works. Apparent emptiness is often essential fullness. What looks like nothing may be the most important something of all. Consider your own experience of time. Memory requires gaps. If you could remember every instant with perfect fidelity, the important moments would drown in trivia. We remember by forgetting, preserving meaning, by letting detail fade. The spaces in memory, the forgetting, are what make remembering possible. Conversation requires pause. A speaker who never stops, who fills every moment with sound, communicates nothing because they leave no room for the listener to process, respond, integrate. The silence between speakers is not failure of communication, but its essential structure. Even thought requires emptiness. Try to think continuously, to fill your mind with unbroken ideation. You cannot. Thought emerges from the spaces between thoughts, from the gaps where processing occurs beneath consciousness. What feels like not thinking may be where the real work happens. The physicist and the artist arrive at the same insight from opposite directions. Emptiness is creative. The quantum vacuum fluctuates because it must, producing virtual particles that occasionally become real. The musical rest resonates because it must, providing the space that makes the next note mean something. The margin exists because it must, creating the structure that allows text to communicate. Perhaps this is not a metaphor at all. Perhaps what we call meaning, in art, in language, in experience, operates according to the same deep principles as physics. Contrast creates perception. Structure requires absence. The something needs the nothing to be something at all. When you next encounter silence, consider, is it really empty? Or is it full of potential? Structurally essential, the creative nothing, without which the sounds would signify nothing. Nothing, it turns out, is everywhere, and everywhere it is, it creates. We began with an invitation. Close your eyes and imagine nothing. You failed. Everyone fails. And now, having travelled from that failure through quantum mechanics, black holes, cosmic origins, atomic emptiness, and the creative silence of art, we can understand why. Nothing may be impossible, not merely difficult to imagine, not merely hard to achieve, impossible, forbidden by the fundamental laws that govern existence. The uncertainty principle demands fluctuation. The vacuum cannot be still. Even the most perfect emptiness conceivable must seethe with activity that cannot be removed, because removing it would require a precision that physics prohibits. Your inability to imagine nothing was not cognitive failure. It was accurate intuition. The universe cannot achieve what your mind cannot conceive. Consider the question that has haunted philosophers for millennia. Why is there something rather than nothing? The question assumes that nothing is the default state, the natural condition, requiring no explanation. Something, by contrast, requires a cause. The existence of the universe demands an answer. Its absence would have demanded nothing. But what if this assumption is backward? What if nothing is impossible? What if true emptiness cannot exist because quantum uncertainty forbids it? What if the vacuum must fluctuate, and fluctuations must occasionally produce structures, and some of those structures must persist? If nothing cannot exist, then something is inevitable. The question answers itself. We do not need to explain why there is something rather than nothing if nothing was never an option. This reframes everything. The universe's existence is not a mystery requiring external explanation. It is a consequence of internal necessity. The laws of physics do not permit true emptiness, so true emptiness does not exist. Something fills every would-be void, not because anything chose to fill it, but because filling is what voids must do. We are not accidents in an indifferent cosmos. We are consequences, inevitable expressions of creative potential that could not remain unexpressed. The vacuum fluctuates because it must. Occasionally, fluctuations nucleate universes. In those universes, structures form. Some structures become complex enough to ask where they came from. We are the universe contemplating its own origin. We are nothing asking itself why it became something. The atoms in your body were forged in stars that existed billions of years before you were born. Those stars emerged from clouds of hydrogen that condensed under gravity from the plasma of the early universe. That plasma emerged from the cosmic inflation that followed the Big Bang. And the Big Bang may have been a quantum fluctuation in primordial nothing. A fluctuation that persisted because its energy balanced to zero. You are a child of creative nothing. So is everything you see, everything you touch, everything you know. The stars above, the ground below, the air you breathe, and the thoughts you think, all may be descendants of the vacuum's restless creativity. Potential that became actual and eventually wandered about itself. This is not mysticism. This is physics, followed to its conclusions. Does it diminish us? Some might think so, to be products of fluctuation. Consequences of uncertainty, rather than intentional creations, seems to reduce significance. I take the opposite view. That we exist at all is remarkable. That we can understand how we came to exist is more remarkable still. The universe is under no obligation to be comprehensible, yet we find, again and again, that our minds can grasp its principles. We are small, brief, fragile. We live on a minor planet orbiting an ordinary star in an unremarkable galaxy, and yet we can trace our lineage back to the creative nothing that may have birthed everything. We are just an advanced breed of monkeys on a minor planet of a very average star. But we can understand the universe. That makes us something very special. The great misconception about nothing is that it is simple, passive, empty. The truth is that nothing is the most dynamic, creative, consequential substance in the universe. It seethes with potential that cannot help but actualize. It produces particles at black hole boundaries. It may have produced the universe itself, and it produced you. When you next encounter emptiness, a silent room, an empty page, a pause in conversation, the space between stars, remember what hides there. Remember the virtual particles flickering in and out of existence. Remember that the vacuum cannot rest, cannot be still, cannot be truly empty. Remember that black holes glow because nothing creates something at their edges. Remember that you are, quite possibly, the creative potential of nothing. Become conscious of itself. We began by asking you to imagine nothing. You could not, because nothing in the absolute sense may not exist. What you imagined instead, the darkness, the space, the expectant void, was already full of creative potential, seething with activity, pregnant with possibility. The vacuum does not wait passively for things to happen to it. It generates, It fluctuates, it produces, and sometimes, perhaps inevitably, its production persists, and structures form, and those structures become stars and planets and creatures that wonder about their origins. Why is there something rather than nothing? Perhaps because nothing was never an option. Perhaps because the uncertainty principle forbids true emptiness. Perhaps because creative potential cannot help but create. Perhaps the question was the mystery all along. The answer was hiding in the question's false assumption. Nothing is not where possibility ends. Nothing is where possibility begins. Remember to look up at the stars and not down at your feet. Try to make sense of what you see and wonder about what makes the universe exist. Be curious, because however difficult life may seem, there is always something you can do and succeed at. It matters that you don't just give up. The universe went to all the bother of existing, and to the further bother of producing beings who could notice, who could ask, who could understand. We are its children, children of creative nothing, descendants of a vacuum that could not keep still. That surely is wonder enough.